Alright, so now let's give you some ideas about how may you summarize or measure the degree of variability of a data set. So trying to measure the variability is somewhat very important if we want to describe a set of data. This is going to help us to understand how the data spread within the range, or what is the dispersion of this data set. This is important especially when the two sets of data have the same center. Okay, for example, for these two, okay, the red line or the red curve is actually a frequency polygon. Okay, it's just that because there are too many points and too many class points, so this looks like a smooth curve. But anyway, yeah, you may imagine that it is a frequency polygon. And then we have two distributions here. They are different, right? You know they are different because we have two curves. And it's because that the blue one is more dispersed than the red one. Okay? They are locating at the same place, but one is more variable than the other. That's why we need to measure variability. The first way to measure variability is to calculate the range. Okay? Suppose I have a set of data like this. Then the range is just the difference between the maximum and the minimum numbers, or notation-wise, we can do this. By this notation, we are asking among x1, x2, x3 up to xn, what's the maximum number? And then among x1, x2 up to xn, what's the minimum number? Take the difference, we get the range. Okay, if the range is small, somehow we say the data are less dispersed, or if it's large, then it looks like more dispersed. Another thing is the interquartile range is similar, but it's the difference of the first and the third quartiles. Okay, in this case, it's the range of the middle 50% of data. Okay, that's the idea of interquartile range. It excludes those extreme points and can give you another measurement about the middle 50% data. So these are two things. Another way to measure variability is through the investigation of each point. For each point, we first calculate how far it is from the center, and then somewhat aggregate all those deviations. Okay, so let's describe deviations. Typically, when we are talking about deviations from the center, we are talking about the mean. Okay, so consider a set of population data. Okay, like this, and let's say we have calculated, or I would say there is a population mean mu, right? Now, the way for us to measure the deviation is very simple. To find the difference between a data point and the population mean. For xi minus mu is just the deviation. Let's see an example. Suppose we have 7 numbers here, and then these form a population. In this case, we can say that, okay, the first number is 1, the second number is 2, the third number is 4, and the fourth number is 5, and so on until 9. In this case, we first calculate the mean. Okay, summing up these 7 numbers, we get 35, and then divided by 7, we get 15. Sorry, we get 5. Oh, that's my mistake. We get 5. And then, what's the deviations? For the first number 1, the deviation is just 1 minus 5, so it's negative 4. And so on and so on. The last number, the deviation is 4. So that's the idea of deviations. If we are talking about sample data, then the deviation should be calculated based on the sample mean. Okay, nothing special. So now, there are so many numbers. Somehow we need to find a way to aggregate these numbers. The first thing to do is to take average. of these numbers. Okay, that's going to be a mean deviations. So let's look at this formula. For I from 1 to capital N, okay, so we are talking about x1, x2 up to xn. For each I, we calculate that deviation from mean. So x1 minus mu plus x2 minus mu plus x3 minus mu, and so on and so on. And then we sum up all those deviations and then divide it by n to get the mean deviation. For this calculation, if we sum them up, immediately we see 0. Okay, we see 0. And immediately we can say, okay, so the mean deviation is 0. Is it always 0? When we change to another data set, will the mean deviation still be 0? Or it's just a coincidence here? That may be an interesting question, but let me give you a quick answer. It will always be 0. The best way to understand it is just for you to modify some numbers a little bit. For example, if you say, that's because it's in symmetry, right? So how about changing 9 to be 10 or 11 or 20 or 30? Things will be different here, of course, but the key is that the mean will also be affected when you change some numbers here. And eventually, there are some smaller numbers, there are some bigger numbers, but the sum of their deviations must be 0. Okay? Some numbers are below the mean, some numbers are above the mean, so of course, eventually everything will sum to 0. So what should we do? This aggregation is definitely useless. So people in general use two ways. Somewhat that's the ways to fix the fact that we are summing up negative numbers and positive numbers. The first way is to take absolute values before we sum them up. Okay? So for each deviation, we take the absolute value. If this negative 4, we convert it to 4. Okay, that's reasonable. And then we sum them up and take an average. So like here, these are deviations. If we take, when we put two bars here, that means absolute values. Okay, absolute values means if it's positive, then it's there. Or if it's negative, then the negation is its absolute value. Or the absolute value can be defined as the difference from that point to the origin. Okay, so here, negative 4 becomes 4, negative 3 becomes 3, negative 1 becomes 1, but the others remain there. So sum of them now becomes a positive number, and then the mean absolute deviation is 2.29, or around 2.29. Okay, sometimes we abbreviate it as MAD. Another way to make negative numbers becomes positive is to do a square for them. Okay, for each deviation we square it, and then negative number is going to become positive. Like here, negative 4 becomes 16, negative 3 becomes 9, and so on and so on. Again, we can sum up all these numbers and then divide it by 7. This is going to give us around 7.43 as our mean squared deviations. In statistics, we give it a special name, variance. Okay, this is a measurement for variability, variance. So immediately you have a question. We have two different ways to measure variability. Will they always be consistent? Okay, that means is there possible to have two different data sets so that in one data set, so that the MAD of the first data set is larger than the second data set, but the variance is the reverse. Okay, we're asking whether it is possible or not. Probably you may think about that for 10 seconds. We have answers later. Another thing that you may want to ask is, if there are two ways to measure, is there a better one? Let's try to answer it. So, at least we may first observe one thing. That's if we have larger MADs or larger variances, then we say that data is more dispersed. Okay, so intuitively, let's look at these two examples. Suppose the first data set is 1, 2, 4, 5, 6, 8, 9. The other is 0, 2, 4, 5, 6, 8, 10. Okay, you can see that the middle 5 numbers are the same, but the first and the last numbers becomes farther from the center. So this data set is more dispersed, right? And then after our calculations, we can see MAD and the variance, they both becomes larger. And eventually that's always the case. When the data set becomes more dispersed, MAD and variances will become larger. So when you have one data set, you may calculate its variance and then compare this variance with the variance from another data set. That's going to help you compare the variability, the relative variability of these two data sets. Okay, that's something we may do. And then immediately there is we can see some differences. For MAD, it puts the same weight on all values, but for variance, it puts the more weight on extreme values. Extreme values is going to affect variance a lot, right? Because it is get squared. So let's see this example. When we have numbers 0, 4, 5, 8, and 10, we can calculate the MAD as 2.4 and its variance as 10.4. If the data is 1, 2, 7, 8, 9, the MAD is larger, but the variance is smaller. Oh, sounds interesting. So let's try to say something about it. For the first data set, is 5 is here, is the middle point. And then we have 0, 4, 6, and 10. Okay, this is how the first data set look like. For the second data set, it's 1, 2, 5, 8. Oh, sorry, this should be 9, and this is 8. Okay, so once we have this, what does that mean? We can see that these two data sets are dispersed in different ways. For the blue one, or the first one, most data are close to the center, but they are extremely far data. For the second one, all those data are somewhat closer to the data set compared to the previous extreme points, but they are all far from the center. So that's why intuitively we can understand for the first one, the variance is larger, okay? Because they have very extreme numbers that are very far from the median, or from the mean. So they have very large deviations, and that's going to contribute to a very large variance. But it's also possible that we have another data set here, such that the variance is smaller, but the MAD is larger. So now we have a conclusion. They may be inconsistent, and they are really two different indicators because they may give you different results or different conclusions. Regarding how to choose them, choose one of them, people use variances more in practice or in research. There are many reasons, but anyway, one of the main reasons is that people tend to believe that variability is really something that should consider extreme points. Okay, and that's also how things works in many different areas. We may discuss that in class. But there are also some situations that MAD is more appropriate, like here, demand forecasting. So I would like to elaborate a little bit about it. why do we say when we are doing demand forecasting, MAD is a better way to measure the mean errors? That must because each unit error of each unit of forecasting error are counted the same. Okay, 1 unit shortage and 2 units shortage. We somehow tend to believe that 2 units shortage is bad, is twice as bad as 1 unit shortage. Okay, it's not that it becomes 4 times bad, it's still 2 times bad. Okay, so you may use this criteria to think about your environments. If a large error really give you a huge loss, then variance would be a better choice. But if in your measurements that does not happen, then you probably should consider MAD. Okay, so we're almost done. One problem about variances is that the unit measurement is the square of the original one. Like for example here, in this data set about heights, if we calculate the variance, it's going to, the number will have the unit of measurement as cm squared. Okay, it's not really meaningful. So people would like to take the square root of a variance to generate the number called standard deviation. Standard deviation is just defined as the square root of the variance. Okay, so for example here, if we take the square root on 34.5, we get this 5.85 centimeters, and this number typically can provide more managerial implications. Standard deviation is a very important measurement when we are doing inferential statistics, because this number is going to tell us a lot about the distribution. Okay, but again, we are not at the stage to talk about it, so just keep in mind, put that in your notes or whatever, standard deviation is very important. Okay, there's one thing that you need to know is about the difference between population variances and sample variances. Recall that when we are talking about population and sample means, we have these two formulas. Looks very similar. How about population and sample variances? They are really different. For population variance, we have something like this. Okay, for each deviation, we square it, sum them up, and then divide it by the total numbers. But when we have a set of sample data, when we are calculating the sample variance, the denominator is n-1, is the sample size minus 1 instead of the sample size. Okay, so n and n-1 is totally different. And then immediately you have this question, why are we dividing this number by n-1? It's because that when we want to use a standard sample variance to estimate the population variance, doing this using this magic number is going to make our estimation more accurate. We will try to explain this later when we talk about this issue again, but at least you need to know the formula for population and sample variance are really different. So if you are doing your calculation, you need to be careful about these two things. Okay, with that, we may also define population and sample standard deviations. Okay, we may take square roots of them, take a square root of them. Here we also have n-1. The notations sigma square, s square, sigma and s are used throughout this semester. And when you are doing any statistical reports, when you write this, people know what's that. The last one is about coefficient of variation. We'll just use these slides to talk about it in this semester, but its concept is simple and maybe very useful. When we are talking about variance or standard deviation, actually we should take the mean into consideration, right? If we are talking about the variance of baseball member heights or the variance about weights, typically we should not compare them directly because the base is just different, the scale is just different, right? We probably want to normalize it with the mean. Then the measurement may be more reasonable. So when that's really something to do, we would like to calculate coefficient of variation. And the formula is very simple. The standard deviation divided by the mean. For example, if we want to calculate the variability of income levels at two different countries, then if one country is much poorer than the other country, we probably should not compare their variances directly. We probably should compare their coefficient of variations. So whether to do this normalization or adjustment is up to you, and you need to decide whether to do this or not. Okay, I think I used too much time to talk about the first four lectures. The first four videos. I used almost 1 hour. So let me try to postpone the discussion about correlation to the lecture. Okay, in the lecture I will find a good time to use about 10 to 15 minutes to complete the last piece of lecture that I should do in videos. I can actually do that, but it's just the first trial, right? So there's no reason to give you so many videos. So I will stop here. I hope you learned something from the video. If you feel that you are not 100% understand, that's fine because we still have the lecture. The video is designed to be complementary to lectures. It's not designed to replace the lecture. So let's see what's going to happen during lectures. Thank you.